Our next speaker is going to present a paper about analysis in sensibility of a motion detection algorithm for selecting noise reduction methods in X-ray image sequences. The authors are Lucas Souza e Silva, F.R. Rocha, L.B. Amaral, C.A. Carneiro, F.M.F. Ferreira, and Z.M.A. Peixoto. And the paper is going to be presented by Lucas Souza e Silva.
Okay, good morning for everyone. My name is Lucas, and I'm here to present you the recent results that arise from a research we conduct at PUC Minas. And the title of our work is Analysis and Sensibility of a Motion Detection Algorithm for Selecting Noise Reduction Methods in X-ray Image Sequences. My work team is here, named here, and this presentation is going to happen in the next 20 minutes. Well, as an introduction, we'd like to talk that the use of X-ray is a technology that is very used in medical, for example, and it leads to fast results to the doctor, analyze the internal conditions of the patient, and it has acquired increased importance because of it. So we can notice that there are very noisy in this kind of images, and it is the motivation of our work. So to acquire better images, for example, we should increase the dosage of X-ray in the patient or increase the time exposure of the patient during the examinations. But it's not desirable because it can lead to the appearance of damage in cells of the patient, and it's not desirable. So acquiring better images without increasing time and dosage is always desirable, and it is the motivation. And to solve this problem, we would like to analyze an algorithm that applies temporal and spatial filtering driven by a motion detection mask, and the evaluation of this method is going to be present here. So this presentation is going to show you a little bit about the noise present in this kind of image, the motion detection algorithm that we evaluated, the hybrid filtering, what is the hybrid filtering that is proposed here, some simulation results, and to conclude in the end. Well, the noise present in this kind of image is named quantum noise or radiation noise, and the major responsible for this noise is the X-ray source, and it's related to a random and non-homogeneous distribution of photons in the surface that receives this kind of photons emitted by the X-ray sources. So it's intrinsic to the process of acquire these images. And about some students that are led in this research, we could find that it can be approximated by a Gaussian distribution, given by this expression, where me and forgot this letter here is the mean and the variance of the distribution of the noise. And having this kind of model of the noise, we could apply some filtering techniques. For example, spatial filtering that is more suitable for dynamic regions. However, temporal filtering is much more for example, it has better results in sequences because it takes, for example, a mean of some pixels located at the same position. But if we have movement, which is our case in our images, our sequences, we can observe that some tracks or some traces appears in the final result. So to increase the results of the filtering, we could detect the motion and apply temporal filtering in the static pixels and the spatial filtering to the dynamic pixels. And the hybrid filtering is the sum of these results. Selection of pixels based on the presence or the absence of motion in each pixel, and to apply the proper filtering technique, spatial or temporal filtering. In the end, there is the composition of the filtered image pixel by pixel, associating spatial or temporal filtering techniques. This is the flow chart that describes our method, and I would like to show the motion detection that is the center of our work that we evaluated, and the result of motion detection is a mask of movement that's gonna link temporal and spatial filtering to the hybrid filtering result. Though this motion detection algorithm starts with the building of the difference image, it's an absolute value. So we take 2 consecutive frames of the sequence and calculate the difference image for these both frames. And afterwards, we define the number of grayscales that need to be chosen. For example, for an 8-bit image, we could, for example, choose 8 intervals, and the intensities of the pixels are allocated in each of these intervals. Step 3, allocation of each pixel of the current noise frame in its corresponding gray interval. For example, if a pixel has a value of 34, for example, we could allocate it in the second interval. And it's our algorithm that we implemented here. We can enter with these values here. And step 4, calculation of the standard deviation of pixels allocated to each gray intervals. This standard deviation is going to be a threshold to choose between movement or static pixel. Step 5, as we have the value of difference image here, we will apply a decision rule. And if the difference image value located at xy, xy, is much more than 3 times the standard deviation of that interval, so we will characterize this pixel as dynamic. If the value of the image difference is lower than 3 times the standard deviation of that interval, it's going to be a static pixel. And in the end of the motion detection algorithm is the composition or the generation of the binary mask, the mask of movement or motion detection mask, that's going to drive the chosen between filtering temporal and spatial. There is an example here where black pixels are the static pixels and white pixels are the motion pixels. So for each pixel here, white pixels is going to be applied a spatial technique, and the black pixels or static pixels is going to be filtered by spatial techniques. So we applied temporal filtering just taking the mean value of the last filtered image and the current value. So it's a recursive technique. And the spatial filtering, it's a mean value between two consecutive pixels in the same row. And the result of the hybrid filtering, the combination of static and temporal, we can see here. And the evaluation of these results is going to be the main contribution of this work. It's going to be present now. So to evaluate this method, we had some real images, real sequences that have been acquired in real condition of these examinations. And as a subjective analysis, we could put here the amount of movement of each sequence. Each row here is a different sequence. And these letters and numbers is going to be present. So here, as I told you, the amount of movement, low, medium, and high, it was a subjective analysis of the sequences. And moving detection sensibility, we could put, for example, A for non-existent, so the motion detection algorithm didn't work for this sequence. And letter D, there was a high intensity movement detection. And those numbers, 1, there was no mistaken detection of noise. In other words, the detection was very successful. Or number 4, excessive erroneous detection of noise in all frames. So the detection was not successful in this case. Taken back to the table, we could notice that the quantity of movement, there is an inverse relationship between the quantity of movement and the number of that gray intervals that have been chosen to the algorithm. For example, for low and medium movement, the better results have been getting with much more gray intervals than the high movement classified here. We could use less intervals, and more intervals implies in more processment and more latence. And the original algorithm didn't apply any of these considerations. So we could see here in this graphic, for example, in this y-axis, we can see the standard deviation calculated by that method, and here the number of that gray intervals. We can notice that for the most values here, there is a pattern which mean value is something about 150. We are using 32 intervals. If we increase the number of gray intervals, for example, 64, this pattern has another mean value, and it decreases to the half. So we conclude that this algorithm doesn't contemplate this kind of limitations, and this threshold that is implied to the algorithm would be more explored in future works, because the algorithm just implies that we should pick this kind of threshold and apply it. But we can see here that if we calculate for less number of gray intervals, we could use the same value to another applications of the algorithm, and not using this kind of characters of the sequence images, we could say that the algorithm has this kind of limitations. And to conclude, the application of hybrid filtering is suitable for this purpose because it increases the signal-to-noise ratio, even not considering this kind of limitations. And it's possible to reduce patient exposure during examination, as well as the radiation dosage, because we can have better images just with the hybrid filtering. And as we present here, there's a relation between the amount of gray intervals and the probability of success related to this better decision rule. It's based on the statistic characteristics of standard deviation. And this algorithm should consider most effectively the characteristics of contrast between the body and the background, and the movement of the image sequences. And we explore some other considerations in the full paper. And the authors would like to thank the graduate program in electrical engineering at PUC Minas and XPro Sistemas that helped us a lot with the real sequences images. And we now time for questions.
Questions? I have a question. You assume that your noise is described by the Gaussian distribution, but quantum noise can also be described by Poisson distribution. Did you consider that?
Yes. As Poisson distribution is a kind of Gaussian distribution, there are some works that assume that Poisson is much more describes better than Gaussian distribution. But we don't consider this kind of, for example, simulations. We just assume that is a Gaussian distribution because a bigger amount of works considered this way. So we consider as a Gaussian because of this. But some works suggest that it's a Poisson distribution. Some of them, but the bigger amount of works are Gaussian distributions.
Any more question? Okay, thank you very much.